Welcome to this session of Energy Conservation and Management. Myself, Anirban Sarkar, Assistant Professor of Mechanical Engineering Department, JS College of Engineering in Kollani, West Bengal. Today, we are going to be discuss about energy conservation opportunities. Energy conservation opportunities, that is the first of all comes is fuel substitution. For a energy efficient industry or economy, identifying the appropriate fuel for efficient energy conversion is very important parameters. Energy generation. Identifying energy opportunities in energy conversion equipment utility such as captive power generation, steam generation in boiler, thermic fluid heating, optional loading of DG set, minimum excess air conversion with boiler thermic fluid heating, optimizing existing efficiencies, efficient energy conversion equipment, biomass gasifiers, cogeneration, high efficiency DG set, etc. That is, after suitably choosing the fuel, what are the energy generation method and how to recover or how to maximize the energy generation, whether by boiler, whether by thermic heat fluid, whether by using DG set, whether by optimizing existing efficiencies. So these we need to be optimized. Next is energy distribution. Identifying efficient opportunities network such as transformers, cables, switch gears, and power factors improvement in electrical systems, and chilled water, cooling water, hot water, compressed air, etc. So energy, how we will distribute it, that is through transformer, cable, switch gears, power factor improvement, that also we need to be, these are the factors that electrical system we need to be improved. Energy uses by processes. This is where the major opportunity for improvement and many of them are hidden. And we have discussed the various processes earlier in steel making furnace, in steel making industry, in cement industry, in glass manufacturing unit. What are the possibilities of heat, waste heat, hidden waste heat recapture or waste heat conversion we have discussed. Now, technical and economical feasibilities. The technical feasibility should address the following issues: technology available, space, skilled manpower, reliability, service, etc. The impact of energy efficiency measure on safety, quality, and production process. The maintenance requirement and spares. The economic viability often becomes a key parameter for the management acceptance. The economic analysis can be conducted by using a variety of methods. Example, payback methods, internal rate of return method, net present value method. For low investment, short duration measures, which have attractive economic viability and simplest method that we need to be identified. Now is the example of sample worksheet for the economic feasibilities. First of all, name the energy efficiency measures, that is, first of all, investment, annual operating cost, and annual savings. So you can see that for an equipment, civil works, instrumentation, and auxiliaries comes under investment. The annual operating cost, cost of capital, maintenance, manpower, energy, and depreciation counts. And annual savings, that is thermal energy, electrical energy, raw material, and pesticides. Now net savings per year, that is estimated, that is annual savings minus annual operating cost. That should be equal to the payback period in months, that is investment per net savings per year multiplying. Now classifications of energy conversion measures. Based on energy audit and analysis of the plan, a number of potential energy savings projects may be identified. This may be classified into three categories. One is low cost, high return, medium cost, medium return, and high cost, high return. Normally, the low cost, high return project receives priorities. Other projects have to be analyzed, engineerized, budgeted for implementations in a phased manner. Projects related to energy cascading and processes changes almost always involves high cost coupled with high returns and may requires careful scrutiny before funds can be committed. These projects are generally complex and may require long lead time before they can be implemented. So now we'll discuss case studies of a industry where combining DG set cooling tower with main cooling tower. So this is the report for energy conservation recommendations. That is, in this case, this is the detailed energy audit we have done in this particular sector. So first of all, title for recommendation, that is combined DG set cooling tower with main cooling tower. Description of existing system and its operations. Main cooling tower is operating with 30% of its capacity. The rated cooling water flow is 5,000 m³ per hour. Two cooling water pumps are in operation continuously with 50% of its rated capacity. A separate cooling tower is also operating for DG set operation continuously. Description of proposed system and its operation. The DG set cooling water flow is only 240 m³ per hour. By adding this flow into the main cooling tower, will eliminate the need for a separate cooling tower operation for a DG set. Besides improving the percentage loading of main cooling tower, it is suggested to stop the DG set cooling tower operation. Energy savings calculations. Capacity of the main cooling tower 5000 meter cube per hour. Temperature across cooling tower, that is 8 degrees centigrade. Present capacity 3000 meter cube per hour. Temperature across cooling tower, that is 4 degrees centigrade at operation. Percentage loading of main cooling tower, that will be 30%. Capacity of a DG set cooling tower 240 meter cube per hour. Temperature across the tower 5 degrees centigrade. Heat load we can calculate, that is capacity multiply into Cp and multiply into temperature difference. So that means total 12 00 000 12 into 10 to the power 5 kilocalorie per hour. Power drawn by the DG set cooling tower, number of pumps and its ratings, that is 2 number into 7.5 kilowatt. Number of fans and its rating 2 number into 22 kilowatt. Power consumptions at the rate of 80% load, that is 22 into 2 plus 7.5 into 2 into 80, that is 47 kilowatts, that is 0.8. Additional power requirement for main cooling tower for additional water flow of 240 meter cube per hour with 6 kg per centimeter square. That is equal to total equal to 7 kilowatt. Now net energy savings, that is 40 kilowatt. Cost benefit, that is 40 into kilowatt into 8,400 hours, that is 336,000 unit per year. Annual cost savings, that is estimated as 13.4 lakhs per year. Investment, only cost of piping, that is rupees 1.5 lakhs. Simple payback method, that is it is recommended that within 2 months it will make up the cost. Next, understanding the energy cost. Understanding energy cost is vital factor for awareness creation and saving calculation. In many industries, sufficient meters may not be available to measure all the energy. In such cases, invoice for fuel and electricity will be useful. The annual company balance sheet is the other sources where fuel cost and powers are given with production related information. Energy invoice can be used for the following purposes. They provide a record for energy purchased in a given year, which gives a baseline for future reference. Energy invoice may indicate the potential for savings when related to production requirement or to air conditioning requirements or space heating, etc. When electricity is purchased on the basis of maximum demand, they can suggest whether savings are most likely to be made. In later years, invoice can be used to quantify the energy and cost savings made through energy conservation measures. Fuel cost. A wide variety of fuels are available for thermal energy supply. Few are listed, that is fuel oil, low sulfur heavy stocks, light diesel oil, liquefied petroleum gas, coal, lignite, wood, etc. Understanding fuel cost is fairly simple and it is purchased in tons of kiloliters. Availability, cost, and quality are the main three factors that should be considered while purchasing. The following factors should be taken into account during procurement of fuels for energy efficiency and economy. First of all, price at source, transport charges, and type of transportation. Quality of the fuels, that is contaminants, moisture content, etc. present, and net calorific value present. Power cost. Electricity price in India not only varies from state to state, but also city to city and customer to customer, through it does not same work everywhere. Many factors are involved in deciding final cost of purchased electricity, such as maximum demand charges, that is in kilovolt ampere, energy charges, that is kilowatt hour, that is how much electricity is consumed, that is TOD charges, peak or non-peak period, that is when electricity is utilized, power factor, that is PF, that is real power use versus apparent power use factor, online incentives and penalties applied from time to time, high tension tariff and low tension tariff rate changes, slab rate cost and its variations, type of tariff clauses and rate of various categories such as commercials, residentials, industrials, government and agriculture, tariff rate for developed and underdeveloped area states, tax holiday for new projects. Next, that is benchmarking and energy performance. Benchmarking of energy consumption internally and externally are two powerful tools for performance assessment and logical evaluation of avenues for importance. Few comparative factors which need to be looked into the while benchmarking externally are, that is scales of operation, vintage of technology, raw material specification and quality, product specification and quality. Benchmarking energy performance permits quantification of fixed and variable energy consumption trends, that is production level, comparison of industrial energy performance with respect to various production levels, identification of best practices, that is based on external benchmarking data, scopes and margin available for energy consumption and cost reduction. Basis monitoring and targeting setting exercise. The benchmark parameters can be, that is, in terms of gross production related. For example, kilowatt hour per metric ton clinker or cement production. Equipment or utility related, it may be percentage of thermal efficiency of a boiler plant. While such benchmarks are referred to, related crucial process parameters need mentoring for meaningful comparison among peers. For instance, in the above case, for a cement plant, type of cement, grain number, that is fineness, Portland, that is Portland, and process are to be reported alongside with kilowatt hour by metric ton figure. For a textile unit, average count, type of yarn, that is polyester cotton, is to be reported along with kilowatt hour per square meter. For a paper plant, paper type, raw material, GSM quality is some important factors to be reported along with kilowatt hour by metric ton or kilocalorie per kg figure. For a power plant or a cogeneration plant, plant percentage loading, condenser vacuum, inlet cooling water temperature would be important factor to be mentioned alongside heat rate. For a fertilizer plant, capacity utilization percentage and on stream factor are the two inputs for comparing while mentioning specific energy consumptions. For a foundry unit, melt output, furnace type, compositions, that is mild steel or high carbon steel or cast iron, etc. Raw material mix, number of power trips could be some useful operating parameters to be reported while mentioning specific energy consumption. For AC plants, chilled water temperature level and refrigeration load are crucial for comparing kilowatt per ton of refrigeration. For a boiler plant, fuel quality, type, steam pressure, temperature, flow are useful comparator alongside thermal efficiency and, more importantly, while thermal efficiency on a gross calorific value basis or net calorific value basis, or whether computation is by direct method or indirect heat loss, may mean a lot of benchmarking exercise for meaningful comparison. For cooling tower effectiveness, ambient air, wet and dry bulb temperature, relative humidity, air and circulating air flow are required to be reported to make meaningful sense. Compressed air specific power consumption is to be compared at similar inlet air temperature and pressure of generation. Diesel power plant performance, that is to be compared at similar loading percentage, study run condition, etc. Power plant performance. It is measured on whether a plant is now using more or less energy to manufacture its product than it did in the past. A measure of how well the energy management program is doing. It compares the changes in energy consumption from one year to other considering production. Plant energy performance monitoring compares plant energy use at a reference year with subsequent years to determine the improvement that has been made. However, a plant production output may vary from year to year, and the output has a significant bearing on plant energy uses. For a meaningful comparison, it is necessary to determine the energy that would have been required to produce this year's production output. If the plant had operated in the same way as it did during the reference year, this calculated value can then be compared with actual value to determine the improvement or deteriorations that has takes place since reference years. So this plant energy performance is measured in terms of production factor. It is used to determine the energy that would have been required to produce this year production output if the plant had operated in the same way as it did in the reference year. It is the ratio of production in the current year to the reference year. So production factor equal to current year production by reference year. Reference year equivalent energy use. The reference year energy use that would have been used to produce the current year's production output may be called the reference year energy was or use equivalent or reference year equivalent for short. The reference year equivalent is obtained by multiplying the reference year energy by the production factor. So reference year equivalent is equal to reference year energy use into production factor. The improvement or deterioration from the reference year is called energy performance and is measured of the plant energy management. It is the reduction or increase in current year's energy use over the reference and is calculated by the subtracting the current year's equivalent and multiply by 100 to obtain percentage. That is plant energy performance, that is reference year equivalent minus current year energy by reference year equivalent multiplied 100. The energy performance is the percentage of energy saved at the current rate of use compared to the reference year rate of use. The greater the improvement, the higher the number will be. Now, there is another thing that is called monthly energy performance. Experience, however, has shown that once the plants had started measuring yearly energy performance, management wants more frequent performance energy information in order to monitor and control energy use on an ongoing basis. So monthly energy performance can just be easily be used for, that is, as an and is reported as an yearly reporting. So monthly energy performance is summarized into yearly energy consumption report. So that's all for this session. Thank you for joining this session.